which is applied for gas turbine power plants. This cycle has 4 processes as shown in the PV diagram. One, two, three, 4 is the Joule cycle. The cycle has 2 varieties of processes, namely 122 and 324 are reversible adiabatics. Which are also known as isentropic processes. Whereas 223 and 421 are constant pressure as seen in the figure. If we draw the power plant also for this cycle, the cycle would be best understood. The flow diagram of the events are shown here like this. Atmospheric air is taken into the C. C for compressor, T for turbine, gas turbine. Gas turbine is a very high speed rotating thermal turbo machine whose rotational speeds may vary in the range of 20 to 25,000 rpm. Air is taken from the atmosphere into the compressor. It is compressed in the process 1 to 2, which is a reversible adiabatic compression, raising the pressure and as well as temperature of air. The high pressure air leaving the compressor now shall enter the combustion chamber, where the fuel is added directly into the air, having the combustion of the fuel, liberating the calorific value or chemical energy of the fuel. The heat liberated due to the combustion of the fuel shall increase the temperature of the air in the process 2 to 3. So 2 to 3 is the actual heat supply process at constant pressure, raising the temperature of the air. So the combustion gases that are generated in the combustion chamber are now at peak temperature of the cycle T3. T3 is the T max or peak temperature of cycle. Now the gases formed in the combustion chamber at T3 shall enter the turbine, where they expand down to the atmospheric pressure, where P4 is P1. P4 is equal to P1 is P atmosphere. Such cycle is open cycle gas turbine. Open cycle gas turbine power plant. Why it is called open cycle? Because air is taken from the atmosphere into the compressor and the gases are expanded in the turbine down to the atmospheric pressure and then exhausted into the gases to atmosphere, and they are exhausted into the atmosphere from the turbine. That is the reason why it is called open cycle gas turbine. Now the cycle could also be indicated on temperature entropy plane. The events, thermodynamic events of the cycle can be seen more clearly even on the temperature entropy plane, that is TS diagram. which is shown like this. 1 to 2 is isentropic compression of air, raising the pressure and as well as the temperature of air in the compressor. 2 to 3 is the constant pressure heat supply in the combustion chamber. The heat supply is due to the calorific value of the fuel liberated after the combustion of the fuel. 3 to 4 is the isentropic expansion of the gases in the gas turbine doing work, and 4 to 1 is the constant pressure heat rejection to the atmosphere by the gases leaving the turbine. So in total the cycle has 4 processes, namely 1 to 2 is isentropic compression of air, 2 to 3 is isobaric or constant pressure heat supply to air, 3 to 4 is isentropic or reversible adiabatic expansion of gases in the gas turbine, 4 to 1 is isobaric heat rejection by gases to atmosphere in the open cycle gas turbine. In total the cycle has 2 isentropics and 2 isobars. Now let us define the pressure ratio of ideal Joule cycle or ideal Brayton cycle as ideal cycle. It is called ideal because all the processes are assumed to be reversible. The pressure ratio RP is defined as pressure of air after isentropic compression divided by pressure of air before isentropic compression, that is equal to RP is equal to P2 by P1. But here P2 is equal to P3 and P1 is equal to P4. Therefore, RP could also be written as P3 by P4, the pressure ratio across turbine. Across gas turbine. The thermal efficiency of ideal Joule cycle can be defined as net work done per cycle divided by heat supplied. But net work done per cycle is equal to heat supplied minus heat rejected according to the first law of thermodynamics. Heat supplied to cycle is in the process 2 to 3, that is at constant pressure. Therefore, heat supplied is equal to Cp into T3 minus T2, which could also be written as H3 minus H2. Why it can be written? Because change in enthalpy of the ideal gas is nothing but Cp into delta T in any thermodynamic process. Here air is ideal gas, therefore change in enthalpy can be written as Cp into change in temperature. Similarly, the heat rejected from the cycle is at a constant pressure, that is 4 to 1. It can be written as Cp into T4 minus T1 kilojoule per kg, which can also be written as H4 minus H1 kilojoule per kg. Therefore, thermal efficiency of ideal Joule cycle is equal to 1 minus Qr by Qs, that is equal to 1 minus Cp into T4 minus T1 divided by Cp into T3 minus T2. Cp could be cancelled off. Now taking the T1 common, it becomes T4 by T1 minus 1. The denominator also taking the T2 common, it becomes T2 into T3 minus T2 minus 1. Now 1-2 process is isentropic or reversible adiabatic. Therefore, we can write the isentropic relation, that is P2 by P1 whole power gamma minus 1 by gamma is equal to T2 by T1. That is equal to Rp to the power of gamma minus 1 by gamma, because P2 by P1 is defined as pressure ratio Rp. Similarly, 3-4 process is also isentropic. Now similarly defining P3 by P4 whole power gamma minus 1 by gamma is equal to T3 by T4. This is also isentropic relation for the process 3-4. But P3 is equal to P2 and P4 is equal to P1 implies T3 by T4 also is nothing but P2 by P1 whole power gamma minus 1 by gamma. This is equal to Rp to the power of gamma minus 1 by gamma. Therefore, combining the above relations, we get T2 by T1 is equal to T3 by T4. Implies T4 by T1 is equal to T3 by T2. Now, considering the thermal efficiency, which is given as 1 minus T1 into T4 by T1 minus 1 divided by T2 into T3 by T2 minus 1. The brackets could be cancelled off. It can be written as 1 minus 1 by T2 by T1. Now it is substituted as 1 minus 1 by Rp to the power of gamma minus 1 by gamma. This is the formula for air standard thermal efficiency of Joule cycle or Brayton cycle. Hence, from the formula we can say that as pressure ratio of Joule cycle, that is Rp, increases, its thermal efficiency also increase. In the Joule cycle, the minimum temperature of cycle is prescribed or decided by atmospheric air conditions. That is, T minimum is decided by surrounding ambient air temperature. The peak temperature or T3 or T max is decided by design and metallurgical limitations of gas turbine blades. Therefore, for a fixed values of T1, that is T minimum, and T3, that is T maximum, which were both decided by the ambient conditions and metallurgical sustainable temperature of the blades. The maximum thermal efficiency is obtained when pressure ratio Rp is equal to T max divided by T minimum whole to the power of gamma by gamma minus 1. Usually, T max, that is peak temperature, is the range of 1000 Kelvin to 1100 Kelvin. Usually in this range, the peak temperature of gas turbine cycle lies, whereas T minimum temperature is in the range of 280 Kelvin to 300 Kelvin. That is the atmospheric air temperatures. Now we shall define work ratio of gas turbine cycle. It is defined as the ratio between net work done per cycle and the turbine work. Work ratio is equal to turbine work minus compressor work divided by turbine work. Wt minus Wc divided by Wt. Here the compressor is driven by the turbine. Usually the type of the compressors what we use in the gas turbine power plants must be of either centrifugal type or axial flow type compressors, which could handle very high volume flow rates or mass flow rates of air. Because in the gas turbine power plants we need large volume flow rates of the working fluid. Hence, only a centrifugal compressor or axial flow compressor is suitable for the gas turbine power plants. Now, if we can calculate the work of compressor as minus integral VdP, because since compressor is steady flow device, the work done in a steady flow process in a reversible process is given by minus integral VdP. Considering the relation, thermodynamic relation, that is TdS is equal to dH minus VdP, since S is equal to constant in the compression process, because the compression is isentropic compression, I can write dH is equal to VdP. Therefore, integral dH is equal to integral VdP, implies work done on air in the compressor is equal to change in its enthalpy. Therefore, work of compressor is equal to H2 minus H1 kilojoule per kg, which can be written as Cp into T2 minus T1 kilojoules per kg of air, where Cp is the specific heat of air at constant pressure. Cp of air many times can be assumed as 1.005 kilojoules per kg Kelvin. Similarly, work output of the turbine can also be given as minus integral VdP, because expansion of the gases in the turbine, they are also isentropic. Work of turbine is decrease in enthalpy of the gases in the turbine, that is H3 minus H4 kilojoule per kg, which can be written as specific heat of the gases into T3 minus T4 kilojoule per kg. Approximately 1/3 of the turbine work shall go for driving the compressor. Only the remaining 2/3 work, approximately 1/3 of the turbine work will go for driving the compressor. Remaining 2/3 of the turbine work will be taken as net work output of the cycle. Now, let us see to know at what pressure ratio Rp the work ratio of Joule cycle is maximum for a fixed values of T minimum, that is ambient temperature, and T maximum, that is prescribed by the metallurgical limit of gas turbine blades, that is peak temperature of the cycle. So fixing the minimum temperature, that is ambient temperature of air, and the maximum temperature that could be permitted in the gas turbine cycle. Now our objective is to know at what pressure ratio of the Joule cycle the work ratio of the cycle is maximum. That could be seen pictorially also on the TS diagram. Minimum temperature is fixed. Maximum temperature is also fixed. Let it be T max. Let this be T minimum. Now we can see so many pressure ratios between these two peak temperatures for the gas turbine cycle. This is one. Here where the pressure ratio is very high, and you can see very low pressure ratio. And the optimum pressure ratio could be like this. Looking at the three cycles for which the pressure ratios are different, very low pressure ratio, in the ABCD and very high pressure ratio in the ABCD and very low pressure ratio in A, B dash, C dash, D dash, and optimum or medium pressure ratio in the A, B double dash, C double dash, D double dash. Which pressure ratio shall result in maximum area? Obviously, the area in the A, B double dash, C double dash, D double dash A shall be the maximum. Obviously, the net area of the TS diagram shall indicate net work done per cycle. Therefore, the area of cycle A, B double dash, C double dash, D double dash is maximum, which is indicating maximum net work done per cycle, which is obviously the pressure ratio corresponding to the maximum work ratio of the Joule cycle. Therefore, for maximum work ratio of ideal Joule cycle, the pressure ratio required is RP opt, that is optimum pressure ratio. Optimum pressure ratio means the pressure ratio required for maximum work ratio. This is equal to T max divided by T minimum whole to the power of gamma by 2 into gamma minus 1. This is the condition for maximum work ratio or maximum net work done per cycle of the ideal Joule cycle for a fixed minimum temperature of T minimum and fixed maximum temperature of T maximum. Both the temperatures are fixed by the ambient air conditions and metallurgical limit that could be sustained or tolerated by the gas turbine blades. Usually T maximum is taken as 1100 Kelvin and T minimum is chosen as 300 K. Now, looking at the conditions for maximum thermal efficiency of ideal Joule cycle and maximum work ratio of ideal Joule cycle for a fixed T minimum and T maximum, we can see that RP max is square root of RP opt, where RP max is the pressure ratio at which thermal efficiency of ideal Joule cycle is maximum, and RP opt is the pressure ratio at which work ratio is maximum. One is the square root of the other for a fixed minimum temperature and maximum temperature. Usually the criteria of choosing pressure ratio in ideal Joule cycle is to keep in mind to obtain maximum work output or maximum work ratio only. The criteria is not maximum thermal efficiency. For example, if you choose T max as 1100 Kelvin and T minimum as 300 K, RP max obtained will be somewhere near 90, whereas RP opt will be the square root of 90. That will be around slightly above 9. But what is the pressure ratio finally chosen? It is only 9 that is usually applied or chosen as a pressure ratio in the practical Joule cycles.